I would like to discuss a little bit arterial filtration. Now, the people who know me know that I have made some presentations in the past on arterial filtration. So what I would like to avoid is to go back to all the physics behind this technology. But I think we have to do a very small review on the main points. And one of the main points is the fact that when a fluid is not moving, every GMI, gaseous GMI, will actually go up. And that's very simple, so when we have very low flows, it's very easy to remove them. But the moment we actually start to move this fluid, and in this case, this would be at the right, so the fluid is moving in this way, you can see immediately the smallest bubbles are actually dragged inside the fluid. And this is a basic concept. We should never forget that if we want to remove them, velocity will be an issue. So we have actually two main forces. We have the buoyancy, which is mainly depending on diameter, meaning that when you have an arterial screen filter, what it will remove very well are big bubbles, around 500 micrometer. But once they become smaller, they are actually captured inside the screen, and they probably will remain there or when they are diffused, or they will pass the screen. And in opposition to what still a lot of people believe, there is no absolute filter available on the market for gaseous microemboli. So what's the basic point of it? And that's important to also keep in mind. It's highly depending on the pore size, as you can see here. If you would have a 40 micron filter or a 20 micron filter, this will, as based on this formula, you can see this will increase the resistance to a gas bubble to go through this filter screen. Another important remark on that is that if we make the optimal filter, this would be a filter probably here with a pore size of 5 micron, because we want to keep all these small GME, but we will all agree this would be a very aggressive filter for the cellular components of the blood. Meaning, and I stress that every time, and I want to stress it also this time, there is a huge difference between hemocompatibility, which we all want, and complete safety, which we all want. They are not actually in agreement with each other. So if you want the most safe system, it will be less hemocompatible. If you want a very hemocompatible system, it might be less safe. So if we make some filtration, MAT, and that's important, because we are overwhelmed with all these nice studies. But a lot of people forget that the way the study is performed is of utmost importance. The majority of them are done in vitro. So we have to keep in mind they are done mainly with water. And as you can see, the surface tension here, it's about 72 dynes. And this gives a resistance, a delta P over the filter, which is around 40 millimeters of mercury. That means these are the data most people take with them home, because this is what the companies are providing us. This is what the majority of studies are providing us. But if you change it just to blood, as you can see immediately, these filters become less performant. And that's one of the reasons why you see that in the initiation of bypass, there is always a small increase in the number of GME which are actually passing this filter. And then if we add even more, for example, a coating, you can see again there is a small but an important decrease of this value. And this is true not only for heparin coating, but also for physio coating. And the worst wasn't at the time plasma treatment. As you can see, if you use plasma treatment, everyone was saying, such a nice device, because now I can prime my filter in 10 seconds. Yes, but it was no longer active in removing GME at the same time. So what are potential sources of GME in our system? The venous reservoir remains number one. And it remains number one because most of the air is actually introduced in the venous reservoir, whether it comes from the venous line or whether it comes from infusions of different sources. Drug administration would be, for example, one of these sources. Then we have assisted venous drainage, which is used more and more, and eventually the impact of pulsatile flow. If we look to the venous reservoir, this is old studies, and we all know that it's better to have a top-to-bottom entry compared to the other way that we come from the bottom. And the reason is that you actually make a fountain which is creating a lot of GME. Now, if you look to the volume, this is also important. You see very high volume here, about 1 liter, very low counts. The moment you actually reduce the volume, the counts increase. But then if you use a different gas, for example, nitric oxide, then you can see that here the counts go down again. So it's not only the gas by itself, but it's also the composition of the bubble, which will be extremely important, and that's very difficult to investigate. So let's look to the reservoir. We have massive improvements in venous reservoirs. I think this was the main breakthrough over the last 5-6 years. We have now several reservoirs on the market which have improved severely. But what remains a problem is what we do as clinicians with those reservoirs. And what you see here is just to filter bleed in the reservoir. So you take the purge line of your arterial filter and you bring it back to that venous reservoir. Actually, what you do then, you splash it. You will not see it because there is all this nice defoamer before it, but you splash it on these polycarbonates. And as you can see, depending on the reservoir, you actually create a lot of bubbles and especially also a lot of very small bubbles. These or part of them will be transferred through your arterial filter. If you generate GME, it's never an absolute filter, you will translate part of it through the filter. And if we actually, in addition then, add, for example, a vent, then you can see that you are worsening the situation. So it's extremely important to understand that if we add something additionally to the venous reservoir, we should really think what is the best location, and that will be different from brand to brand. But we are so focused on these open reservoirs. Still, the majority in the world is using open systems. I'm come from a region where it's the opposite. In the Benelux, we are using more closed systems than open systems. And we should really consider it because, as you can see here, look to the huge difference in bubble generation in favor of a closed system. This is also probably one of the reasons why a lot of these MEAC systems in their different configurations do very well. So we have to keep in mind an open system. We can improve it, but it remains an open system with all the interactions of an open system. And I was very pleased with one of the previous speakers because he made this excellent survey. We have no real idea what's happening in Europe on arterial filtration. And what I liked was that there is at least some change from which is an increase of the integrated arterial line filters. Why am I so pleased with that? Because it actually forces you to position the filter in the correct place, being as low as possible below the level of the patient. If we visit whatever center in the world, you still can find a lot of centers where the arterial filter is at the same level of the patient, and then it will give no protection in case of gross air. So this arterial integrated filtration, it actually forces you to use it in the correct position. But what intrigued me even more was this slide, where they actually showed that about 70% actually agrees that we do not have scientific evidence. So we should learn to ask ourselves, why are we doing something which was based on old information, but nevertheless no one of us dares to set up this study? The reason is legal, but I learned now that there are still regions where they are using a lot of CPB systems without filtration. Maybe we should set up such a study and see if there is indeed a difference, yes or no. Because if you look to the data, these are data from my own center. You can see the reservoir is actually still the major component of generation of bubbles. And then we have here a membrane oxygenator on one side and an independent or a separated arterial filter on the other side. Now, let's enlarge this a little bit. What you can see that the protection, whether you have a filter or not, at the level of 40 micron is extremely small. And there is only a very minor difference in favor of an additional filter if you go up to, let's say, about 20 micron. So we can really question, is this worth the benefit? We can also question, what is the best, integrated or non-integrated? So here you can see exactly the same slide, but this time we have a separate filter with the same unit, and then we have the integrated version. Let's enlarge it again. And as you can see, both filters are actually performing exactly the same. So that's not the issue. The only benefit of the integrated system is the correct positioning, but in efficiency, it's exactly the same. But is this the answer? Because what we forget is, if you have a screen, if you actually push air through that, you can also fractionate this air. And there is some evidence, like this study which was performed by the same group, where you can see that actually it seems that you have sometimes higher counts of smaller bubbles after the screen, which could make sense because you actually allow these bubbles to go through all these fibers, and then they finally, when they are in their smallest form, they are actually coming into contact with the screen. We can still question whether we have the correct position having this filter at the end of the oxygenator. And then, of course, almost every study performed will show you that there is a benefit of this integrated filtration. However, I'm not always convinced that the hypothesis or the conclusions made by some authors are completely correct. For example, what you see here, those people state that if you look at those two oxygenators, they work as a depth filter, and those two work more as a screen filter. This is not true. It can't be true. All of them work like a depth filter. But what could be a difference? The difference is that these oxygenators have a much larger surface area, meaning that the velocity, and remember, velocity is extremely important in drag, will be lower in these units. And so they will be, in a certain way, a better bubble trap compared to the other two. Because a depth filter, and that's often forgotten, it works by interception and by captation. That means a particle, whether that would be a bubble or a particle, it will be actually adhered by this fiber. And you can imagine if you increase velocity, these bubbles, because of the shear which you will actually create here, will be dislocated and will then go further through the fiber stack. And this is extremely true. As you can see here, this is the particle diameter. The larger the particle becomes, the more easy to capture it. So again, this is in favor of probably repositioning filters when the bubbles are still bigger. Let's look then to vacuum-assisted, because that's another technique we are using more and more, and we can question again, is this always safe? What we do know is that the position of the catheter is extremely important, because what you normally do, if this would be the vessel, we actually have a certain velocity. Once the blood is coming inside this catheter, the catheter size is smaller, we will increase velocity. If you change the energy balance, there is something else which has to go down, and in this case, that will be pressure. So if we look at this, if we would take a 28 French, we would have a flow of 3.5 liters, for example. Then at the side holes, we would have a negative pressure of about 2.5 millimeters of mercury. If we, in this patient now, would decide for whatever reason, we want to increase the flow, and now what we actually are going to do, we are going up to 5 liters. Then you will see that this negative pressure almost triples, meaning that what we can do is a collapse of the vein, and this can happen, for example, because the patient is still partially ventilated, and you have this positive pressure, which is actually pushing on the caval vein. And the moment it actually collapses, that will create bubbles, because what you actually do, you will take bubbles out of the fluid, especially when you use any form of hyperoxia. So the question is then, how can we do it safe? Well, the first thing we have to keep in mind, if you have gravity drainage, then in general, the bigger the cannula, the better will be the drainage, because you're limited by the maximum negative pressure which can be generated. This is not the case whenever you use assisted drainage, meaning that what you actually have to do, you have to bring it to a size where there is a compensation for the higher velocity inside the catheter and the higher negative pressure. And it seems that this value is around 0.5 up to 0.6 of the original diameter of the vessel. And that's important to keep in mind if we want to control GME during vacuum assist or kinetic assist. We have to look to the correct positioning and the correct diameter of the vessels. If you do that, then there is no real difference in the amount of GME, as was shown in this study. And this is an interesting study because it's one of the few which has been done with blood. Because I can show you totally different results once you're using another fluid, for example, like a crystalloid or whatever. So it's very nice to see there is a slight impact, but it's a relatively marginal impact, probably because also the positioning was done in a perfect way. And what if we then combine the worst situation? We combine vacuum assist together with pulsatile flow. The problem with pulsatile flow is the fact that you create extremely high velocities for a short period of time inside the fiber bundle, meaning that the depth filter function normally will be disturbed if there is micro air present in this bundle. Now, what you can see here is that indeed, as we increase the flow, there is an increase, whether you have pulsatile or non-pulsatile, of the amount of micro bubbles, which makes sense because these are depth filters. They work like that. They only perform very well if you have very low velocities. But the interesting part is if you then have additional vacuum assist, the impact is relatively marginal. However, a big flaw of this study is it was done with water. And I'm not sure that we can extrapolate these values into the clinical practice. And finally, we should not forget, we build a system. If we have a MEAC system, what is one of the big advantages? We are forced to use a validated system. If you do not want to use that, then you have to do your validation by yourself because every component is validated, but not the complete system. And as you can see here, although it's an older study, I still like it a lot because you can see that there are differences depending on the circuit and the different components in there. So meaning, we should not rely only on the industry and say, oh, I have a lot of GME, this is because of brand A, B, C, D. No, we should also question, did we bring these components inside integration with each other in the most optimal way? Can we really be saying that we have validated these components? And to show you the importance of that, we have this study from Bob Groom from the US, who actually start changing things in his circuit. And the huge change you see here between this situation and this situation is just a change from a 120 micron venous filter inside this open reservoir down to a 40 micron venous filter. So what you actually see here is just the higher performance of the smaller pore size in the venous side. This had a huge impact in his setting on the total system. This is one component. You can mostly buy sometimes both. It's really worth rethinking this issue. And then, of course, a lot of young people are actually entering perfusionist, and they want to become a perfusionist. However, very often, we train them on the spot. And when I go to several centers, you can see the extremes. You are centers where they actually have to do some cases where there is a very good tutoring. People are actually following every action and are discussing it with the students afterwards. But there are circumstances where students, after a few months, have to work alone, even in emergency cases, because of staff, lack of staff, or other problems. And we should be aware that the perfusionist by itself, it's also an important cause of GME generation. And for example, in this study, they were looking by TCD to the brain vessels. And as you can see, this is the situation where everything is going smooth. Nothing is happening. It's during the cross-clamping, so there is not a lot of things that normally will happen. Now the perfusionist starts to work. He's adding some drugs, and immediately you can see there is a lot of activation inside the field. But even worse, now there is air coming through the venous line. And this air starts to be captured at one spot in the line, so it doesn't make a big impact on the drainage. But as long as it is present, it will fractionate all the time. And as you can see, you have a huge impact now, which will take at least minutes. So we can really wonder if we should tolerate this, yes or no. And that it is important was also shown in this study. They were looking to several perfusionists in the same center and to the number of times they just purged their line on which they were taking samples. And as you can see, there is a very nice correlation between the number of purgings, splashing every time, and the GME generation in the system. So we should be aware that also our personal responsibility is important. So what are the conclusions of my talk? I still believe that the reservoirs are key, but they have improved. What is not improved is our knowledge sometimes on where we should put some purging ports inside the system. Remember, a purge which contains almost no air, as for example a filter purge line, the best position is inside the venous line. If you put it on whatever other place, you generate more GME than you actually remove by the filter. We do know that GME removal by oxygenators and filters exists, and that it exists at certain levels. But we need more research to see what is the best combination of having good mass transfer, good GME removal, but at the same time not at the expense of hemocompatibility, because that's another important issue in our older population today. And then finally, the good news is when you use VAVD and pulsatile flow or VAVD alone, and you work according to the known standards, it not necessarily means that you increase the risk for GME generation in the patient. Thank you very much for your attention.
Thank you for an excellent talk. Are there any questions from the audience, please? And please introduce yourself with a name and country, please.
Tim Jones, Birmingham, UK. Great talk as always, really enjoyed it. You partly sort of covered this in your closing comments. Are you suggesting that the benefits of an inline arterial filter could be completely lost if you have a purge line, which most necessitate do have purge line running back to a open reservoir system, and we know that's a source of generation of GME. So in fact, having an arterial line filter with a purge line permanently open, as traditional teaching tells us to do, in fact is worse than probably not having an arterial line filter at all. That'll be the first question. The second question is, if we are going to run with that setup, should we therefore now shut the purge line unless we're going to sample during the case?
These are excellent questions, as always. I hadn't expected otherwise from you. But I think it's indeed true that if you have the purge line open and it's on the venous reservoir, I'm convinced you generate more GME than you actually remove. Because what is forgotten by a lot of people is that 10 micron, 20 micron, 30 micron, 40 micron, they are not actually get out of the filter. They are not purged. They remain against the screen. So actually they are removed by diffusion over time. So the only ones, they are the bigger ones, will be going through the purge line and the reservoir, which is, let's be honest, that's probably a very low number based on whatever data are available. So if you keep that in mind, and we know, you have seen the results, if we have the splashing, there we know we generate those small bubbles. So actually we are saturating in a certain way this screen with all these small bubbles, and we need more diffusion time to remove them. So yes, I believe that we should reconsider this. And if we want to keep it open continuously, it should be on the venous line and not on top of the venous reservoir. And the second question, because that I forgot. Okay.
More questions? I'm not a perfusionist, but and you have a huge knowledge in this field and experience. Is there anything on the horizon, any advances in techniques or developments that you can see in the closest future regarding this GME in the production of venous filters and so? Is there anything?
That's a difficult question. I think that for years, the vulnerable part in the circuit was certainly the venous reservoir. I think everyone would agree on that. But I have to say the industry has taken the message, and now we have several companies who have markedly improved GME removal in their venous reservoirs. However, as long as we keep an open reservoir, based on its working principle, we will generate GME, that's for sure. And if you want to remove that, we have to rethink going to MEAC systems, going to other approaches that's open for discussion, but then we have to go further than just looking at the different components. For the oxygenator, I'm not always convinced that what we do now, actually sort of an attachment of an arterial filter to the oxygenator, that by itself solves the problem. The benefit of it is that it gives us the correct location, and it's a forced location, you cannot change it. So that's certainly a benefit. But I'm still not convinced that it should be at the end where you have the smallest bubbles. So you could really question if we would have it, for example, just before the fiber stack, and we remove it there, then the smaller ones will be captured inside this bundle and probably will be better removed than now, because after they pass the screen now, there is nothing which will remove them beside the tissue of the patient.
Okay. one more question, and then we will.
Yes,
proceed,
thank you very
please.
much, Philippe. Christian Mateve, Belgium. You got me confused here, which is great. Would you consider using an arterial filter, or for that matter, between the pump and the oxy? Is this something that would be feasible?
It has, as you know, it existed in the past. That could be one solution. But the question then is, how should that filter look like?
Right.
Because I can tell you, based also on experiments we did ourselves, if there is air coming in such a screen filter, and it's partially captured in this filter, at that moment you start generating huge amounts of micro air. And it's basically because this filter screen becomes dry, and there it will pass. So it's a perfect method in actually generating GMA. So I'm not convinced that this is the best place. But for example, I think what you would be a distribution fan, where you first get the possibility for air to reduce the speed and to get removed, and then in a second phase, you would have, for example, a screen or a woven pot. You can discuss whatever should be best. That would probably be the better solution.
You said that the screen filter would have the same filter capability as a depth filter, or a depth filter the same as a screen filter. Although a depth filter has multiple layers, is this not seen in whatever investigation you have done?
I think there is a misunderstanding. I didn't say that they are as good. What I said is that the working principle is different. In a depth filter, it can only work at very low velocities.
Right.
That's the only way it can work. And then you can discuss how many layers you put in there, but the basic principle is it has to be at low velocity. Okay. That's the reason why they introduced screen filters, because a screen filter is not vulnerable to that. But a screen filter is less performant in actually removing GME. And this was known from the early days, because there are very old articles already showing that a depth filter, which existed at the time as an arterial filter, was the best performing one in removing all air. But why did they stop? Because it also took all the platelets out of the blood. So again, the story comes back. The best safety is not hemocompatible, and vice versa. We need to find the in-between, which is acceptable for both arguments.
So the multiple layers in an oxy, would you consider this as a depth filter or not?
I'm sorry. Now. We are over time, and you have to take a question afterwards.
Oh, sure.
Yeah.
Great.
But
Thanks
thank
for
you. Excellent
me out
questions, but we have to proceed. Thank you very much.
I want to introduce the next speaker, Mr. Koons from the King's College Hospital in